And let's do a share screen. And let's hope that the share screen will work. Does it work? I think it is. Can you see my screen? Okay, yeah. Good. So what we're doing the weak interaction. So last time we discussed several properties that are unique to the weak interaction that differs from the strong and the electromagnetic interaction. So the two properties we discussed is one is the quark mixing, right? So the weak interaction, the charge current weak interaction can mix quarks from different generations. We cannot have that from leptons, but we can have it for quarks, right? And that leads to the CKM matrix, right? To the Cabibbo angle and the CKM matrix. And then the second thing, which is unique, is disparity violation. So we learned about the parity operator, and it was thought to be a symmetry of nature until it was discovered in the 1950s that it is not, that the weak interaction does not conserve parity. We discussed the vectors and axial vectors. And we saw in the weak interaction from the count decay, the count can decay into a 3 pion state. Count minus can decay into pi minus plus pi plus plus pi minus with a parity of a -1, and also to a 2 pions, or to a pi minus plus a pi 0 with a parity of +1. So initially it was thought that these are two separate particles that decay. They didn't realize that it's the same count. They call them the theta and the t and the tau, but we know today it's the same particle. And that means that some of the particles come up only with right-handed or left-handed helicity states, right? So for example, the neutrinos, right, they always in nature have a left-handed helicity. Right, H neutrino always a -1/2 neutrino. And of course, for the anti-neutrino, it's always a positive. Of course, the same rule applies for the other generations of leptons. So there is something in that breaks the symmetry. I told you that it might somehow be related to the symmetry breaking in the DNA, but I don't know much about it. It was a big surprise when it was discovered. So what we want to do now, I want to go, first I give you sort of a hand-waving argument about the masses of the bosons, of the gauge bosons in the weak interactions, and then we're going to describe the Lagrangian of the weak interaction. Unless you have any questions. No questions? Okay. Okay, so the masses of the gauge bosons, just kind of a hand-waving arguments. Masses of the gauge bosons of the weak interaction. Right. So another important property of the weak interaction, which discriminates it from the electromagnetic and the strong interaction, is that the gauge bosons are massive, right? The gauge bosons of the weak interaction are massive, right? Both them gauge bosons of the electromagnetic, right? The photon, and the gauge bosons of the strong, the gluons, are massless. Now, interestingly, this fact was known even before they were actually detected, right? They were detected only in the 70s, but people knew about that or anticipated it, that they're massive, way earlier. And it was deduced essentially from two facts of the weak interaction, right? So the two facts are, one, it is weak. And two, weak. And two, It only operates at small distances. Short distances. Right? If it was, let me go over that carefully. So let's look first at the weakness of the interaction, right? Weakness. And how is that related to the fact that the gauge bosons are massive? So remember the Feynman rules that we discussed earlier in the course, right? There were two relevant Feynman rules, right? One is that in each vertex, Feynman rules. Feynman rules, relevant. The first is that in each vertex, we have a coupling constant G, right? At each vertex, there is a coupling constant. And for each internal propagator, we have a term which goes as 1 over q squared minus m squared. Right. So if I look at the typical weak interaction, what would be a neutron decay, beta decay. Right. So a beta decay, right? We have a neutron that goes into a proton plus electron plus antineutrino. Right. So if I draw the Feynman diagram, neutron is made of two down quarks and one up quark. Right. Now the down quark, one of the down quark undergoes a beta decay. Right. So exchange to an up quark. This is a, sorry, I'm writing, this is a proton. Right, and the W quark by itself then decays into an electron and an antineutrino. So if I just look at the diagram, right, I have the two vertices, right? It's clear because we have conservation of momentum in each vertex, then must have that the q squared, right? This is q, remember just, right, this is just the p e mu plus p neutrino mu squared, right? Now, because we have conservation of energy and momentum, and obviously the q squared must be smaller or equal than the mass of the decaying particle, right? So it's essentially it's a virtual particle, right? So we have an m w squared needs to be much greater than q squared, which means that the amplitude of the process, right? The amplitude would go as g squared, which is just the alpha weak, divided by m squared, because we have this 1 over q squared minus m squared. And m is much greater than q. So it should go this over m squared, mw squared. Which means that the rate of the process, what happened? I think it's just a, is it? Yeah, I think I just touched the cable here. Which means that the rate of the process, when gamma goes as alpha weak squared divided by mw to the power 4. Now remember, a rate, right, has units of 1 over time. So in terms of units, it's just a unitless, I told you it's a hand waving argument. Units of rate right? It's 1 over T, right? Which means, right, and time is the inverse of the energy. So I must multiply it by another unit, another term, which will have unit of energy to the power 5, or mass to the power 5, to get the correct dimension. So to get the correct dimension, by a term with units of mass to the power 5. Now I'm going to do, without making any calculation, right? The only natural quantity that we have here, right, is that it has would be the mass of the decaying hadron, right, the neutron. That's the mark that we can have. You can think of the mass of the quark if you want, but that's going to be less. Right now, of course, this is not really the case, right? I have to actually consider everything: the mass of the daughter particles, the mass of the the wave function, the spins, whatever. I'm just elegantly ignoring all of that, right? So I'm just left off with the mass of the neutron just as a dimensionless, just to get the right dimension. It means that to get the right dimension, one must have the decay rate to be proportional to alpha weak squared times mass of the neutron to the power 5 divided by mass of the W to the power 4. That explains why this is so weak, right? Because we have two terms here, right? Alpha weak, which is much more than 1. And mass of the W is much greater than the mass of the neutron. All right, it's a very hand-waving argument, but just to give you an order of magnitude. And again, this is argument which was used way before the W and Z bosons were actually discovered. Used, or people used, right, was about the range of interaction. Now, the electromagnetic force is unique because it operates at, very large distances, right? But the weak interaction is not something which we feel. It's something which acts on the size of the kernel. Why is that? So again, I'm going to use an argument which is a very old argument. It is not the way we're seeing it right now. It's an argument that was used by Weak back in 1938. And he was looking at pions at that time. They knew about pions. And he used Heisenberg's uncertainty principle. Right. So the idea that Weak was using is basically the following. Suppose that we want to measure the energy of the W particle, right, when it travels from one vertex to the other. It's a bit using a new notation in kind of an old terms. So in order to produce that, right, we must supply energy to the W boson, which would be at least the mass, right, mc squared. But of course, this energy does not exist in the process, right, because the mass of the neutron that decays is much smaller than the mass of the W boson, right? Which means that the W can only exist up to the uncertainty principle, right? Which means that it can only exist over times of 1 over m, or 1 over e, right? Because delta E times delta T must be greater than something. And let me just write down in that way. So in order to produce W, right, one must supply energy E greater than m W. No. Now this energy does not exist. Right, because the neutron is smaller than MW. Which means that using the uncertainty principle, W exists only at times, right, shorter than 1 over MW. So the distance it can travel is also, right, is T. So the maximal range of interaction that we can have for the weak interaction is of the order of 1 over MW. Now, if we write down this in meters, which what we know today as the known mass of the W, so the radius in real units, right? C over MWC squared is, from what we saw at the beginning, roughly 0.9 GeV times Fermi divided by 80 GeV, which is equal to 10 to the minus 3 Fermi, or 10 to the minus 18 meters. It's not surprising the size of the kernel. Now, note that I'm using different terminology that is commonly used today, right? Today, we don't say that the virtual particle violate conservation of energy, right? We simply don't say that anymore. Rather, we argue that energy and momentum are conserved in each vertex, right? But the thing that is violated is the mass of the particle, right? We said that the W, being a virtual particle, does not sit on the mass shell. So it's a different terminology, which is essentially describing the same thing. Of course, the way we do it today makes it much easier to make calculations using the Feynman diagrams. But of course, the argument of limited interaction range is not affected. So you can think of it in both ways, I guess. Either that the virtual particle, it always conserves energy and momentum, but then the mass cannot be fully determined, or that you know the mass, but then the time in which it lives is confined by the Heisenberg's uncertainty principle. It's the equivalent way of thinking of the same thing. All right. Okay, now let's talk about the Lagrangian of the weak interaction, and here things get slightly more complicated and way more beautiful. That's going to lead us to the Weinberg Glashow-Salam Weinberg model, GSW, the Lagrangian of the weak interaction. Okay. So here we have some problems. The first problem that we have, we wrote down the Lagrangians of the electromagnetic interaction of the strong interaction, but we had no problem because the gauge bosons were massless, right? But here we do have a problem because we do have a mass break of the gauge bosons and they break the symmetry of the Lagrangian, right? Mass problem, the mass of gauge bosons, breaks the symmetry. So what do we do? For right now, what we're going to do, we're simply going to ignore the masses of the gauge bosons. And then next week, I'm going to show you what's known as the BEH. That's called the BEH. So the Brute, Engert, and Higgs mechanism to get the mass without breaking the symmetry of the Lagrangian. I'll show you that it gives mass to everything, basically. Gives mass. And now, we simply ignore the mass. So assume that the gauge bosons are massless. Now, all the interaction we studied so far, right? We had an interaction term between the fermionic part and a gauge boson, right? And they all had the same form. It was like a psi bar gamma mu psi a mu, right? This is the interaction term. In the fermion and gauge bosons. Right? That's what we had in the electromagnetic part. So we want to have the weak interaction Lagrangian look the same, roughly. So we expect weak interaction Lagrangian to look more or less the same. But we have a problem here. What's the problem? What is the problem? Which we didn't have previously. Can I simply write such a term?
We need to call left velocity modes of particles.
Right. This term does not discriminate between the left-handed and right-handed particles, right? But we know that the charge interaction, the charge current interaction does discriminate, right? The neutrinos do not interact. Only the left-handed neutrinos interact. What happens here? Right. So the problem is that interaction term must reflect the fact that we're only coupling left-handed neutrinos. Interaction term only interaction term must reflect the fact that the charge current interaction only operates on left-handed neutrinos. Left-handed helicity states of neutrinos, to be more precise. Now, can we use the left-handed helicity state? No, we cannot. Why cannot we use it? Because it's not Lorentz invariant, right? We have the Lagrangian. Lagrangian must be a Lorentz invariant. So the helicity state is not particularly good, right? The helicity state is not Lorentz invariant. Remember that the Lagrangian must reflect all the symmetries that we have in the, in the physics. Particularly also so there's no point writing terms in the Lagrangian that are not Lorentz invariant. But, so what's the solution? We do have a quantity which is Lorentz invariant, and it coincides with the helicity for the case where the particles are massless. And neutrinos are nearly massless, so we can argue that they are massless, at least for the theory. What is this quantity?
Chirality?
Chirality, very good, right? But we show that for massless particles, right, the helicity states, I can even color that. Right, the helicity states are identical to their chirality states. Right? And chirality is Lorentz invariant. So we can write the Lagrangian using chiral eigenstates, which is what we're going to do. So we write the Lagrangian using chiral eigenstates. Oops, what happened again? Oh. Is it, okay. I think I'm touching with my hand on the cable. It connects them. So. Now, just as a reminder, right? We discussed the chiral eigenstates when we discussed the the fermions in the Dirac, when we discussed the Dirac equation, right? So the left and right handed chiral components of a fermion. Just as a reminder, right? Recall left and right handed chiral components of the fermion, right? You know them as psi L and psi R, right? PL psi, this is PR psi. Right, this is just half 1 minus gamma 5 psi. This is half 1 plus gamma 5 psi. Right. Now I just realized I put it down on my lecture notes, but I did not have time to cover that. Simply because of lack of time. But you can read it on my lecture notes, which I posted on the course website. If not, then you just have to believe me. It's actually not that difficult to prove. I actually thought I might give it to you at home. That the two following quantities are vector and axial vector, which we discussed last time. So the quantity psi bar gamma mu psi is a vector. And psi bar gamma mu gamma 5 psi is an axial vector. Now, I didn't prove it in class, but it does appear in my lecture notes because I wrote it down and I skipped that because I'm short of time, as I said. But you can read it in my lecture notes, or much better, you can derive it yourself. It's not a difficult derivation, if you get the idea. So I urge you to try to prove it yourself. See how they change under parity. Which means that if I take a current, so take a current, which looks like left-handed current, psi bar gamma mu, and then 1/2 1 minus gamma 5 psi. It has exactly the form that I'm looking for, which is some constant times a vector plus another constant times an axial vector. Which, as we said, this is exactly what we're after. Because this quantity is not conserving parity, right? It's not conserving parity. So it's not an eigenstate of the parity operator, right? But that's what happens in the weak interaction. The weak interaction does not conserve parity, right? So we can look for an interaction term, which will have the form, which will be J coupled to the W. So interaction term of the form, so we're after. So we want an interaction term of the form J mu L W mu. Now we say, because this is contained in both a vector and an axial vector, we say that the weak interaction has a VA structure. Okay, that's a technical term which you might have seen, or you may see it one day, right? We said that the weak interaction has a VA structure. Right, it's a vector, axial vector. Now, I can actually write it down in an easier way. So I'm going to use the fact, well, let's do a small algebra. I'm going to use the fact that PL squared is just PL, right? The projection operator, the left-hand projection operator. And then the anti-commutation relation between gamma 5 and gamma mu. And the fact that gamma 5 dagger is just gamma 5. All these we showed when we discussed Dirac. And then we write down the current JL mu, right? What's really written here, right, is just psi bar gamma mu PL psi, right? It's PL psi, right? So this is psi dagger gamma 0, and then gamma mu and PL I can double, which now I can take PL and use the fact that gamma 5 anti-commute is gamma mu, right? So I can write it down as psi dagger PL dagger gamma 0 gamma mu PL psi. But this is just psi bar the left component, the left projection of psi, gamma mu psi L. So we have that JL mu contains only the left chiral states of the fermions. right? Those in psi and psi bar. Share with yourself. That means, right, that when I write it like that, right, I write the current like that, and this current couples to the W, right, which is what we have here, right? The charge current weak interaction operates only on the left chiral components of all fermions, right? That's exactly what is written here. The charge current weak interaction operates only on the left chiral component of all fermions. Right. Now for the neutrinos, right, assuming that they are massless, right, this component is exactly equal to the left-hand helicity state, so that's why they interact with them. Right. For other fermions, which are massive, well, neutrinos are massive as well, we know today, but people didn't know that at the time that, in the 1960s, when this theory was written. Then the charge current couples only to the left-handed one. All right. Now let's talk about the gauge symmetry. So remember, we discussed the Wales approach, which argued that all interactions originate from gauge symmetry. So we saw that for the electromagnetic, it was the simplest one, was the U1. For the strong interaction, it was slightly more complicated, it was the SU3, but the mathematical structure was identical. And it turned out that for the weak interaction, we can also specify a gauge symmetry, which is the SU2, but it's SU2L. So SU2, it's a bit in between the SU3 of the strong and the U1 of the electromagnetic. The L is to remind us that the this group operates only on the left-handed chiral fermions. So for the weak interaction, the symmetry group is SU2L. That's from the left hand. Now, being a symmetry, right? It has a name. This is called the weak isospin. So don't confuse it with the flavor isospin that we saw in the tutorial, right? But there are two fundamental differences, but let me write them down one by one, so not to be confused. Right. Flavor isospin. Right. When we spoke about the flavor isospin, or isospin for short, right? Isospin was a symmetry of the strong interaction that acts on the space that is spanned by the mass eigenstates of the U and D. right? And SU2 symmetry of the strong interaction that acts in the space that is spanned by the UV mass eigenstate. Now the weak isospin is also an SU2 symmetry, but now it acts on the space that is spanned by the U and D prime, right? Eigenstates in the weak interaction basis, right? Weak interaction. Right? SU2 symmetry that acts on the space that is spanned by U left and TL prime eigenstates in the weak interaction basis. Of course, it's the same symmetry is copied to the other spaces, right? C, L, and S prime L, and then again T and B prime. Right? Of course, the 3 more times for the leptons. Now, similar to what we did with the spin and with the strong interaction isospin, right? We denote the main quantum numbers by I, and the component by the 3 axes, which are arbitrarily chosen by I3, right? All the left-handed fermions, right? They're eigenstates of the weak isospin, and they can be organized by doublets, right? Having isospin of I half and I3 plus minus half. So all left-handed fermions can be organized by doublets, having I of 1/2 and I3 plus minus 1/2, right? Now the upper number of the doublet, the way it's being organized, right? Its convention is that the upper one is always the particle which differs from the down one by +1 unit of electric charge, right? Relative to the low one. So a convention, right? The upper member of the doublet has 1 unit of electric charge more than the down member. Right, so the doublets, right, would be the neutrino and the E minus left, right, and of course copied neutrino mu and muon left, and neutrino tau and the tau left, and then for the quarks, right, would be the U, but E prime, right, it's in the interaction basis. Left, C, S prime, left, and T, B prime, left. Okay, B prime, S prime, and B prime are related to the mass eigenstates by the CKM matrix. Right, we wrote down the quarks specifically in the interaction basis. I'm sorry for that. Now this common ordering is useful because you know, we want to be consistent with the physical definition of the W boson, the W plus and W minus, which we're going to show you in a few minutes. Now the right-handed particle chiral states, right, are placed in the weak isospin as singlets, right? So for the right-handed states, right, they all have I equal to 0 and I3 equal to 0. Right? E minus right, mu minus right, tau right, and then U, C, T, B, S, and P. Now, just as you know, as a note, the standard model does not require to have right-handed neutrinos. We don't need them. Now we know they do exist, right? Because we know that neutrinos, there are evidence that neutrinos do have mass. So they must have some right-handed neutrinos, so we can add them to the list. So we can have neutrino E right, neutrino muon right, and neutrino tau right. So by the time this standard model was written, these were not known to exist. Today we know they exist, but we don't care about them in that sense, that they don't add much and they don't take much from the description. Now, all these states, right, these are not affected by the SU2, by any rotation in the SU2L space, right? Rotation meaning there is a coupling between the W. Right? These do not couple to the W's, so they're not affected by any rotation. Right? Not affected by rotations in the SU2L space. Right? Which is equivalent of writing down that these guys do not participate. They do not participate in the weak interaction. Okay, you're all with me? Yes, no, maybe? Okay, now we said we're talking about the gauge symmetry. So, if you're to talk about gauge symmetry, let's look at the left-handed Fermion Angle states, right? So each doublet we can write in a compact form, right? So for example, the first generation, and let us write the first generation in a compact form. Right, so psi L, I'm going to write as neutrino E and E minus left. Now I'm going to do exactly what I did for the QED and the QCD, right? Namely, I'm going to argue that this doublet obeys a local gauge symmetry, which means that the Lagrangian has to be invariant under local phase transformation. Okay, so identical to what we did in QED and QCD, we require the Lagrangian to be invariant under local gauge transformation. phase transformation. You have the form, right? Psi equals to psi prime, which is EIG weak, right? The coupling, and then tau dot chi psi. Now the symmetry group here is SU2, right? What are the generators of the SU2 group? I think we discussed that, but maybe I didn't emphasize that. What will be the generators of the SU2? I mean, tau are the generators here, right?
Pauli?
The Pauli. Exactly, very good. So tau, it's actually for the normalization purposes, the tau is half the Pauli. So the three generators of the SU2 group, right? In the 2D representation, this 2D representation, right? And sigma simply the Pauli spin matrices. And the chi's, right? Chi's are exactly as we did. These are the three functions that specify, how much we go in each direction, right? So they specify the exact transformation we want to do. Right? Three functions specifying the local phase. At each space-time point. Okay, so this is the local phase transformation. And we want gauge invariance, right? So what did you do last time? Do you remember to ensure gauge invariance? What did we do to ensure that the Lagrangian is invariant under this local gauge transformation? We took the Lagrangian. If we just take the Lagrangian and apply this local transformation, it's not going to be invariant. We're going to end up having a different Lagrangian, right? So what did we do to ensure that the Lagrangian is invariant? We did some trick. According to Whale, what was the trick we did?
We changed the derivative operator.
Very good, thank you. Guys, I actually asked you a question, I actually needed to answer. That tells me a lot if you can answer or not. Right. So what we did, so to change the derivative to a covariant derivative. Right, you all remember that? Then why didn't you answer? Okay. So to ensure gauge invariant, of our gauge invariance, right, of the Lagrangian, change the derivative to covariant derivative. So d mu becomes a d mu, which is just d mu plus I g weak tau dot w mu. I'm going to explain to you that in a second after I correct my typos here. G mu, or GW, right? These are the coupling constant of the weak interaction. It is, it's not big, it is the coupling constant of the weak interaction. W, I wrote it as a vector. These are the three gauge bosons. Now there are three such bosons because we have three generators. And they multiply the three Pauli matrices. And because of that, there are three, it's kind of custom to denote them as a vector, right? Rather than using indices. Remember that we did it in QCD, we used indices. Right, so here we denote them as vectors because there are three. Which multiply the three Pauli matrices. It just you know, it's a notation, common notation. Right? It's customized. It's custom. The right properly. Custom. We denote them by vector. Now, similar to what we did in QCD, again, basically I'm repeating one by one the steps we did there, right? The gauge bosons transform under gauge transformation, three gauge bosons transform as W, transform as W mu minus D mu chi. That's what we had previously, right, in the EM as well. But then there is this extra term, which comes from the non-commutative of them, right? Remember the structure constants. It will be G W chi cross W mu. Now, why is it a cross term? Because the structure constants of the SU2 are just the Levi-Civita symbols, right? The origin of the cross product is that the structure constants of the SU2 group are just the Levi-Civita tensors. Yeah. You're all familiar with those, right? Is there anyone here who is not familiar with that? Is there anybody here who is not familiar with that? Is everybody familiar with that? Yes. Yes. Okay, so if we write down this covariant derivative and the kinetic term for the gauge fields, then we can write down the Lagrange for the weak interaction. which is going to be gauge invariant. Right, L D sum over all the quarks, right? Psi bar L I gamma mu d mu minus m quark psi L minus 1/4 W mu nu W mu nu, where again W mu nu, very similar to the QED, will be the kinetic term for the W bosons. So W mu nu A is defined to be d mu W mu A minus d mu W mu A minus G weak W mu cross W mu. A, right, is 1, 2, 3. This is the 3 gauge bosons that we have there. Right. Don't get confused, right? The index, the upper index mu, right? X mu. So this mu, right? This represents the component of each vector. Right. So the first thing we find is it's similar to what we had in the QCD. We find that there are vertices with 3 and 4 bosons. So the bosons can interact with each other. There is one thing we haven't done yet, is to associate this W that we find. Right, again, we got this gauge bosons which ended up from the requirement of gauge symmetry of the Lagrangian with the physical particles. So let's try to associate the different W's with the physical particles. We'll associate the W terms with physical particles. So in order for us to do that, we have to look at the interaction term. So the interaction term up to there is an I square, which is -1, so I just throw it away. Right. Up to I squared, which is -1. So there's a minus sign there. If you go over carefully at home, you see that I threw away a -1 in case you were wondering. So the interaction term will look like G weak, right? And then we had the psi bar L gamma mu, and then we had the tau dot W, right? Mu psi N. Right, remember we had the J mu, J dot W. Right. So if you write it down, that's going to be G W, and then psi bar L for the first generation, right? It's neutrino bar and electron bar minus left, right? Then we have gamma mu. Now I'm going to write down explicitly the tau. Tau, as we said, is half sigma, and sigma is the Pauli matrices. So I have 1/2. And sigma dot W, I'm just going to expand them, right? Remember what are the sigma, the Pauli matrices? It's going to be W mu 3, W mu 1 minus I, W mu 2, W mu 1 plus I, W mu 2, and then minus W mu 3. And then psi L is just neutrino E and E minus L. Right? So let's work it out. So this is 1/2 GW. Then we have neutrino E bar minus L gamma mu. And then we have W mu 3 neutrino E. And then plus W mu 1 minus I W mu 2 electron. And then W mu 1 plus I W mu 2 neutrino minus W mu 3 electron. L, all that. So again, let's multiply everything here. We have 1/2 G weak, right? And then we have neutrino bar, gamma mu, W mu 3, neutrino E, all that L. That's L as well. And then we have a minus E bar, L, gamma mu, W mu 3, E minus. And then we had the interaction, the mixed terms, right? That mix the neutrino and the electron. So this would be plus neutrino E bar left gamma mu, W mu 1 minus I W mu 2 E. Then plus E bar left gamma mu, W mu 1 plus I W mu 2 neutrino E left. So we have two terms with the W mu 3 that couples the electron to the electron and then neutrino to the neutrino. And we have two terms which couple the electron to the neutrino, right? Now we know that the terms that couple physically, the terms that couple the electron to the neutrino are the W plus minus, right? So we can identify right, or the linear combination W mu plus minus is 1 over square root of 2, W mu 1 minus plus W mu 2. And this would be the particles, right, that are responsible for the interaction between the left-handed electron and the left-handed neutrino and vice versa. So again, we identify this combination. We identify this combination, right, with the physical W plus minus particles. Quite cool, isn't it? Now, just as a small note, right? How do we know which is the W plus and which is W minus, right? So you can think of the neutrino, right, as an operator that destroys an initial neutrino, and as an E as an operator that creates E bar, right? It's an operator that creates a final electron. And W is an operator that destroys the initial W. Right. If you have a Feynman diagram, neutrino left, right, and a W minus, and end up with an electron, left one. Or you can think of the neutrino as something that destroys the neutrino here. W is something that destroys the W, and the E bar is something that creates the electron. All right. So we ended up with two physical W's, which came out of this model. Again, it's still incomplete. We know that they are incomplete because we didn't put the masses. We still are massless. I'll put the masses next week, or maybe even on Thursday if we have enough time. I think we have enough time, so we'll start doing it on Thursday. There is a third neutral current goes on, right? Which one is that?
Z.
The Z, right? Where is the Z here? What does the Z do? Does it carry any charge?
No.
No, right? So what does it couple?
Only neutral or.
Right. So it can couple neutrino to a neutrino, right? Or an electron to an electron. So where is the Z here? See a zero. I've lost all of you by now, huh? Where is the Z? Come on.
Isn't the Z neutral?
What?
Isn't that the neutral ones?
Yeah, that's what I was expecting somebody to say. Right. I mean, I would at this point I would imagine people to say, okay, we have the linear combination of the W1 and W2 to become the W plus minus. We have still the W3, right? And this 3 is exactly what couples the neutrinos and the electrons. So why not associate the W3 with the Z? Well, there is a good reason why I cannot do that. What is the reason? So it's quite tempting to identify the W3 with the Z. But I cannot do it. Why not? What's the problem?
Is it the different sign between the neutrino and the electron term?
The different what?
The different sign, the minus sign,
No,
the
no,
relative sign.
No. No, they're nothing to do with the sign. Did I mix the sign here? I think I didn't, but check it out. Maybe I made some mistake with the sign. No, I didn't. No, I think it's okay. I don't think I mixed the sign. Or if I did, I should go over everything I did. It's something in the experimental, let's say. Something doesn't match with the experiments. What is the W3 here connect? Well, by construction, you're seeing all these L's around you, right? This is to remind us that all these interactions only connect left-handed chiral states, right? But experimentally, so remember, all the right-handed chiral eigenstates, they don't participate in that at all, right? But experimentally, the Z boson does connect the right-handed states, as far as we know. Now, I should say that all this model was written by Glashow, Salam, and Weinberg. This is the GCW, Glashow, Salam, and Weinberg model. It was written in 1961. That was way before they knew about neutral currents. They didn't know it existed, the Z boson at the time. I'm not sure it was 61. Well, sometimes in between 1960 and 1965. I don't remember the exact year. But it was around that time. And the Z boson was discovered only in 1973 in CERN. It's an experiment called Gargamel. You can go and Wikipedia it or Google it. So the main problem why we cannot do it is because if we were to do that, then we couldn't get that the Z boson couples to the right-handed fermions. So that leads us to what's called the electroweak unification. So the W3 couples only left-handed. Excuse me, I'm a little bit sick. Fermions, but experimentally, the Z couples to those left and right-handed particles, fermions. Again, remember, we didn't know that. They didn't know that, well, they didn't discover the Z back in the 60s. So it was Glashow that had a suggestion to solve this problem. Now, what was Glashow's suggestion? That goes back, this goes back to 61, so I'm sure this model was in 61. Right. It's actually written here on the on my screen. What did he say? We know that the Z is neutral. W3, sorry, is neutral. Right. We have another neutral particle. What is that? What is the other neutral gauge bosons that we have? It doesn't carry anything. Any charge?
Photon.
Photon.
Oh, very good. Right. So you just said, right? Maybe we can take these two neutral bosons, right? We can express all the terms, you know, as a mixture between the photon and the Z boson. Right? So basically, what it does is merging together the weak interaction and the electromagnetic interaction, right? And mixing them together into two more fundamental interactions. So basically it's saying, look, maybe the Z and the A, right? These are mediators, the two mediators of the neutral interaction are actually formed themselves by some linear combination that mixes the gauge bosons of the two gauge theories. All right? So the Z is not the W3, there is a W3, and then there is another, right, gauge boson, which we did not discuss. And a linear combination of both of them give us the Z and the photon. That means that there must be some other symmetry which we did not discuss, right? That gives us this extra missing gauge boson that combined with the W3 would give us the Z and the photon. This is called a hypercharge. So let me write this all down. Now, the really amazing thing is that Glashow did all that before they knew about the existence of the Z boson, so they couldn't really measure it. And then we'll show you next week how we get a way of giving mass only to the Z, but not to the photon. It's quite cool. So Glaser proposed to express it is possible to write the Z boson, the photon and the Z boson in terms of quantum states formed from two neutral bosons. Right. So one of them will be the W3 associated with the SU2L symmetry. And the second one would be another one, which means that we have to replace the U1 electromagnetic gate symmetry with a new gate symmetry, which we call it U1Y. And that's going to give us another one, which is called B, which is going to be associated with the U1Y gate symmetry that replaces the electromagnetic U1 gate symmetry. So we got a unification of the weak and the electromagnetic interactions. Okay. And then he says that I should write down, right? Both Z and A are formed by a linear combination that mixes the gauge bosons of the two gauge theories. Simply beautiful. That's what we look for in physics, right? One theory which merges everything. So we wrote down the U1 EM gauge symmetry is being replaced by, it doesn't exist, U1Y. That's a hypercharge, local gauge symmetry. Right. Now this new gauge symmetry, right? It looks exactly the same as the QED, but it has a different physical meaning. Right? Looks the same. But has a different physical meaning. Right. So the local gauge symmetry would look like, and let me write it down. Psi of x would go as psi of x, which is some unitary matrix, which is E, I, and then the coupling constant is G prime. That's why it's called G prime, and then Y over 2, capital Y, chi of x, psi. So we have a new coupling constant, G prime, and we're going to get a new gauge boson, or a new gauge field, which we're going to call it B, just because A is already occupied. So new coupling constant. A new gauge field. Now the gauge field, right? The new gauge field is going to be coupled to the fermions via a new kind of charge, which we call the weak hypercharge, and denoted by Y, right? The new gauge field comes to the fermion via a new kind of charge. It's called the weak hypercharge. This is the term. Call it Y. And the interaction term, right, is going to look exactly, in terms of mathematics, it looks identical to what we had previously. Just going to call it G prime Y over 2 gamma B psi, right? The interaction term.
ילדים, מה נשמע?
בסדר?
בסדר. איפה אתה? אני בבית, כן.
Okay. So it has the exactly same form as we had for the QED interaction term, right? For the U1 gauge symmetry of the QED interaction term. Right? U, E, gamma, mu, A, mu, psi. Right? Looks exactly the same. Only difference is that QE, right, is replaced by G prime Y over 2. And that's another way of saying that every fermion carries a charge Y, right? Similar, we said every fermion carries a charge E, electromagnetic charge. Now it carries a hypercharge Y, all right? Can be 0. You all with me?
What does capital Q mean?
Does what?
Capital Q.
It's there is a physical electric charge and there is a coupling constant, which we call it E. Well, that's what you measure.
Okay, thanks.
Right. So it's exactly the same. Now remember that in when we spoke about electrodynamics, right? Then the electron carries a charge of -1. Fermions quark carry a fractional charge, right? 1/3, -2/3. Neutrinos carry 0. So now they carry a hypercharge. But now it mixes. So this and the covariant derivative, right? So the covariant derivative comes d mu is just d mu plus I g weak tau dot w mu plus I g prime y over 2 b mu. So now we have two symmetry terms, right? So one is the SU2 and left, and the second one is the U1 Y hypercharge. And we have total of 4 gauge bosons, right? 3 W's and 1 B. Okay. So we merged the weak interaction, which has the SU2 symmetry group, and the electromagnetic, which has the U1. Isn't that cool, guys? Right. And then when we do that, let me just do it, and then I think it's a good time to stop. Well, there's still way to go, but I won't finish it today, right? Then we can write down the photon and the Z boson as a linear combination of the new vector field B mu and the neutral one W3. Then we can write down that A mu, well, it's just a linear combination, so it's B mu cosine theta W plus W mu 3 sine theta W, and Z mu is minus B mu sine theta W plus W mu 3 cosine theta W. Theta W is the weak mixing angle. It also has a name. It's also known as the Weinberg angle. So theta W is the weak mixing angle. Or the Weinberg angle. Now it may look like some arbitrary, but it's something which is easily measured, and much more astonishingly, we're gonna run into this Weinberg angle again when we will speak about the Higgs mechanism and the masses of the W and the Z bosons. It's gonna come out as something which might look very surprising at first, but the masses are not arbitrary. They're related by this angle. So it's not arbitrary at all. And so just, let me just want to do one more thing, right? So if we take that, using this Weinberg angle, and we can write down the fermionic currents, which are associated with the photon and with the Z boson. So the fermionic currents right, J mu electromagnetic is just J mu Y cosine theta W plus J mu 3 sine theta W, and J mu to Z is just minus J mu Y sine theta W plus J mu 3 cosine theta W. And J mu 3 is what we had previously, half GW neutrino bar left gamma mu neutrino L minus E bar left gamma mu E L. Which is quite cool because we achieved exactly what we wanted. All right, I'm running out of time. I won't have, it's not that we are like, we were 2 minutes away from finishing. Okay, we're not, we need another 15 or 20 minutes or maybe more to finish that. But I think we can stop here and then we can proceed. Let me see. Okay, I'll let these things sink in because I think it's getting more and more interesting and more non-trivial. You know, do yourself a favor and go and review all these things before the lecture on Thursday. On Thursday, I'm going to finish with that, and then we'll do some tutorial. And then if we have time after all that, then we'll start doing the Higgs. If not, then we'll just have 1 week for the Higgs, which will not be enough to cover everything, but will give us something, some feeling of how the Higgs work. Okay, any questions? Do yourself a big favor and review this material. It's I can see that it's getting more and more vague in some of yours. I'm not speaking about everybody, but I'm pretty sure that some of you guys are a bit got lost on the way. So now is a very good timing to make sure that everything is clear, because also what we do now is kind of relying on what we did previously in the semester and kind of merges all this together into one coherent picture. So try to make sure that, you know, if there are gaps or anything in your knowledge, now is the time to fill them up. All right. Then have a good rest of the day.
I have two general questions, vaguely related to that.
Yeah.
First, I know that they say this symmetry, this electroweak symmetry, it appears more prominently in high energies, and that it's somehow broken to weak and electromagnetic forces in low energies.
Yeah. You're talking about a different thing, which we will not have time to discuss this semester, unfortunately. This theory works as excellently in low energies. In what you talk about is grand unification theory, right? Which and the running coupling constants, which is something which I mentioned at the beginning, but I didn't really have time to discuss as I thought we didn't have time. It's unification of the couplings. We have here, basically, we have here different couplings. We have the Y, right, or G prime, and G weak. And there are, for us, these are just coupling constants which are not related to each other. Just numbers, which we don't have any way of telling them. If you go to high energies, as we said, these coupling constants are not really constants. They are depending on the energy. So they do, well, people do believe, because there is no full evidence, that they become the same number at a certain point. You go to high enough energy. I guess that's what you're talking about.
Makes sense. Thanks. And one more thing, does that mean that both the weak neutral currents and the electromagnetic force affect right fermions more weakly than left fermions? Because they're a mixture of something that affects both of them at the same rate and something that affects only one of them?
Yes, essentially, you know, the fields of the Weinberg angle is something which is measured, and is measured experimentally. Remember, all this theory, it's great to give you a unified mathematical structure for what we're seeing, right? This is there to explain the experiment, not vice versa.
So I'm asking, in the experiment, does the Z boson couple both right and left fermions, but couples the left fermions more strongly?
No, I don't think so. But this is something which I have to check experimentally.
Because do you understand why I ask? Because it seems like the conclusion from this concept.
No, that's not necessarily the conclusion, because that depends on the value. What I said is that rather than thinking of the Z boson as equal to W3, in which case it will only couple to the left-handed fermions, I think of it as a mixture of W3, which only couples to the left one, and a B, which couples to both of them. So I think actually from when I think of it right now as I speak, I think that you're right, and it will couple more strongly to the left one because you have you're breaking the symmetry. But to be on the safe side, I would want to check this because I don't remember by heart the answer.
Sure, thanks. Thank you. That's it for me.
Okay. Any further questions? Cool stuff, isn't it?
Yes.
It was worth waiting all the semester to get to this stuff now. But I don't think we could have done it before, right? We had to go through everything else before we get here. All right, so we'll proceed with that on Thursday. I also want to tell you a few more things about the experiment, because it's also part of that, so that I'm putting in the tutorials. So we'll have kind of a busy lecture on Thursday, and we don't have that many more lectures to go. So see you all on Thursday, and stay healthy and safe.
Thank you. See you.
Bye.
Thank you.
Bye-bye. Thank you.
I can stop recording.